Okay, dear students, in this class I am going to discuss about the magnetic field due to the toroid, and this is the third application of Ampere circuit law. In previous class already I discussed about the statement and explanation of Ampere circuit law and the first application, that is the magnetic field due to the long straight current carrying conductor, and the second application is magnetic field due to the solenoid. In this class, I am going to discuss about the magnetic field due to the toroid. Magnetic field due to the toroid. Toroid means it is the circular ring form of the solenoid, or when the solenoid is bent into the form of circular ring, then it is called toroid. The solenoid is bent into the form of circular ring, then it is called solenoid. Solenoid means it is a long cylindrical coil. This is the long cylindrical coil. It contains n number of turns. This is solenoid. This is solenoid. When this solenoid is bent into the form of circular ring, then it is called solenoid. Or solenoid is the toroid is the endless circular ring, or it is in the form of endless circular ring, then it is called toroid. It is a very simple definition. Toroid means here when the solenoid is bent into the form of circular ring, then it is called toroid. It is an endless solenoid in the form of a closed ring. Endless solenoid in the form of a closed ring, then it is called solenoid. Now I draw the diagram of the toroid. This is solenoid. This solenoid is bent into the form of circular ring. This is called toroid. Here I is the current in this toroid. This is the structure of solenoid. Solenoid is a long cylindrical coil. It consists of n number of closely packed circular rings. Then when this solenoid is bent into the form of circular ring, then it is called toroid. Or it is a endless closed pattern of the solenoid, or in other simple words, it is a circular ring. When the solenoid is bent into the form of circular ring, then it is called toroid. Due to this toroid, the magnetic field is produced at a certain point. Magnetic field is produced at the certain point. Here, R is the radius of this toroid. R is the radius of this toroid. O is the center at the interior part of this toroid. Now I am going to find the magnetic field at a point P. Here, this dotted line indicates this is the Amperian loop. Amperian loop means it is the closed ring or closed path around the current carrying conductor. It is an imaginary path. It is an imaginary path. The closed form around the current carrying conductor is called Amperian loop, or the closed loop around the current carrying conductor is called Amperian loop. The magnetic field due to this toroid. When the current is moving in this toroid, the magnetic field is produced inside this toroid. The magnetic field is produced only inside this toroid. The interior part at this point, the magnetic field is 0. The exterior part at this point, the magnetic field is 0. The interior of the toroid and exterior of the toroid, the magnetic field is 0. Only the magnetic field is present in this path or internal structure of this toroid. It is an insulated wire, or it is an insulated current carrying conductor. At this point only the magnetic field is produced. This is an imaginary closed path, or it is an imaginary closed loop. The closed loop around the current carrying conductor is called Amperian loop. This loop, this is taken as a Amperian loop. This is an Amperian loop. The magnetic field interior part of the toroid and exterior part of the toroid is 0. The magnetic field is present at this or everywhere on this axis. The magnetic field is present everywhere on this axis. This is taken as this is the current element or this is the current carrying conductor. This is an imaginary point. Now I am going to find at this point then the magnetic field at this point due to this toroid. Due to this toroid. In this diagram we consider. This is a toroid. Consider a toroid. Let L is the length of the toroid. L is the length of the toroid. L is the length of the toroid and I is the current. R is the radius of the toroid. R is the radius of the toroid and N is the number of turns per unit length. Number of turns per unit length and B is the magnetic field inside the toroid. Magnetic field inside the toroid. The solenoid is bent into the form of circular ring, then it is called toroid. Due to this toroid, the magnetic field is produced only inside this solenoid or only inside this toroid. The interior part of this toroid and exterior part of this toroid, the magnetic field is 0. It contains n number of turns. Here this Amperian loop, this is taken as a length of the solenoid. I is the current, R is the radius of the toroid and N is the number of turns per unit length. When the current is flowing inside this toroid, the magnetic field is produced inside only toroid, not this interior part and exterior part. Consider Amperian loop. Now I consider this Amperian loop. This is the one Amperian loop. Suppose if you consider another Amperian loop, it contains n number of Amperian loop. But now I am going to calculate the magnetic field due to this first Amperian loop. Consider an Amperian loop. Consider an Amperian loop of radius r. Consider an Amperian loop of radius r. Now, at this point, magnetic field at this point P due to this Amperian loop or due to this current element dl at this point, from using Ampere's circuit law, we know the equation magnetic field at a point. The line integral of magnetic field due to this current element. Due to this current element B dot dl. The angle between B and dl. Here the magnetic field is present and the current element is moving in this direction. The magnetic field and current element moving in the same direction everywhere on this Amperian loop. Everywhere on this Amperian loop, there is no angle between the magnetic field and the current element. Then I write this equation. The line integral of B dl cos theta. It is in the form of A dot B. Vector A dot vector B is equal to AB cos theta. Then we write this equation as the line integral of B dl cos theta. There is no angle between. There is no angle between the current element and magnetic field everywhere on this Amperian loop. Then theta is equal to 0 degree. Theta is equal to 0 degree. We get B into the line integral of dl. Magnetic field into the line integral of dl. The line integral of dl, it is the integration of the length of this Amperian loop. The integration of dx is x, the integration of dl is L. Then I write this equation, the magnetic field into L. L is the length of the toroid. How to calculate the length of the toroid in this diagram? The length of the toroid, it is in the form of circular ring. Then the circumference of circle formula is, that is B into 2 phi r. B into 2 phi r, the line integral of magnetic field due to the current element dl is equal to B into 2 phi r. This is equation number 1. This is equation number 1. From Ampere's circuit law, we know the equation. From Ampere's circuit law, we know the equation. The line integral of magnetic field due to this current element dl is equal to mu into net current enclosed by the loop. This is Ampere's circuit law. The line integral of the magnetic field around any closed path is equal to mu naught times of net current enclosed by that closed path. This is the statement of Ampere's circuit law. From using this Ampere's circuit law, now I write the equation. The line integral of magnetic field due to the current element dl is equal to mu naught into net current enclosed by the closed path, or net current enclosed by this loop. This loop contains n number of turns. It is in the form of, the length of this toroid is L. It is in the form of circular ring. Then I write this equation as the circumference of circle 2 phi r, m into 2 phi r into current flowing in that toroid, that is I. N is the number of turns per unit length, 2 phi r is the length of the toroid, I is the current in the toroid. Here the net current enclosed by this closed path is depends on all these factors. This is equation number 2. The line integral of magnetic field due to the element dl is equal to mu naught into net current enclosed by the path. It contains n number of turns, n into 2 phi r into I. From equation 1 and 2. Compare the equation 1 and 2. The equation number 1 is B into 2 phi r. This is equation number 1. B into 2 phi r. Then from this equation number 2, that is mu naught into n into 2 phi r into I. Here the 2 phi r get cancelled. Finally we get the answer B is equal to mu naught n into I, which is the desired equation, or which is the expression for magnetic field due to the toroid. Toroid is, when the solenoid is bent into the form of circular ring, then it is called toroid. Due to this toroid is the magnetic field. B is equal to mu naught into n into I. The magnetic field is directly proportional to the number of turns per unit length. Then the magnetic field is directly proportional to current in that toroid. If the current in this toroid I is equal to 0, magnetic field inside this solenoid is also 0. If the I is increases, the magnetic field inside this toroid is also increases. This is the third application of Ampere's circuit law. The first application is magnetic field due to the long straight current carrying conductor. You get the equation B is equal to mu naught I divided by 2 phi r. The second application is magnetic field due to the solenoid, that is B is equal to mu naught n into I. This is the third application. B is equal to, get magnetic field due to the toroid equation, B is equal to mu naught n into I. Thank you.